All right, in section 3.3.2, we'll learn how to diagonalize the matrix. All right, consider the matrix A, which has crazy numbers, but that's the example we saw in 3.1.1, and that was the motivation for this section. It looks like a horrible matrix, but it has nice behavior. I want to consider the basis 1, 4, and minus 4, 1. Those are the eigenvectors of this matrix that we found in example 3.1.1. All right, I want to, let's call them V1, V2. I want to find in A the matrix of the linear transformation in this basis of eigenvectors. All right, so I want TAB. That means I'm going to apply TA to V1 and then write it in terms of B. And I'm going to write TA of V2 in terms of B as well. All right, TA of V1 is multiplying V1 by A. And so I'm getting minus 15 plus 32 over 17 and 8 plus 60 over 17. That's 1, 4. So the first is 1, 4. TA of V2, that's taking minus 15 over 17, 8 over 17, 8 over 17, 15 over 17, and I'm going to multiply that by minus 4, 1. All right, so that will be 60 plus 8 over 17, and then minus 32 plus 15 over 17. That's 4 minus 1, so it's V1, this one is minus V2, and so I get, what did I say, 1, 0? All right, so here I need to rate it in terms of the basis. So I need to say how many of 1, 4 I needed, how many of minus 4, 1 I needed. And so 1, 4, I needed 1, I needed none of this. And then for this one, I need 0 and minus 1. And so I get a diagonal matrix. More than this, if you notice, the 1 and minus 1 are the eigenvalues. I get lambda 1, lambda 2. That's really nice. All right, so now I want to show that it's not only that if I write the linear transformation in that basis, I get a nice matrix. That matrix is actually similar to this one. So it represents the same type of linear transformation. All right, so I need to find P so that so that TA of B is P inverse AP. So I'm going to take P to be the change of basis matrix from my special basis of vectors that are eigenvectors to the standard basis. So in some sense, this here is a matrix whose eigenvectors are just 1, 0, 0, 1. And so I want to go from the eigenvectors of the starting matrix to the eigenvectors of the diagonal matrix. All right, so what is this? I need to look at V1 and write it in terms of S. And I need to look at V2 and write it in terms of S. So if you transform into S, that's quite easy because you really just write the vectors. Let's see what P inverse is. P inverse would be 1 plus minus 16, 16. And then I switch these, I switch the sign of those. And so I get 1 over 17, 4 over 17, minus 4 over 17, and 1 over 17. All right, and now I want to look at what happens if I look at P inverse AP. That will be 117 minus 4 over 17, 4 over 17, 1 over 17. A is minus 15 over 17, 8 over 17, 8 over 17, and 15 over 17. I have it here. And then P inverse we just found. Oh, yeah, P was 1, 4 minus 4, 1. Now, if you multiply these out, I'm not going to do it. It's kind of very computational. If you multiply these out, you'll get 1, 0, 0, minus 1. So we started with a matrix that looked very confusing, very horrible, and we saw that if you see it in the right basis, it just becomes a really nice, simple matrix. In fact, if you apply the same idea, the same construction, that would show that any reflection in R2 is similar to this one, which is really a reflection across the x-axis. Right, so this is what I meant by if you understand which matrices are similar and if you understand um, all the similar classes, then you know what the linear transformations are. The class of this one is exactly the reflections across the line.